But I want to start off today by reminding you what we were talking about last time in the development of high-order schemes. Okay, these are called high-order schemes. They allow us to go second, third, or fourth order in space, or even higher. And the strategy to design those schemes was to assume a profile for the variation of the dependent variable phi, assume a profile inside the cell. You can assume any profile you want as long as the integral of that profile gives you the average value that we store at the cell center, okay? And last we discussed was the K scheme, which combines a bunch of other schemes like second order upwind, quick, third order upwind, etc. Okay? And the idea was we defined two slopes, an upwind slope. So again, remind you of this nomenclature for those of you who were not here. Please go through the video last time because this nomenclature is very important. But just to kind of remind you quickly, we're adopting an alphabetic nomenclature rather than a numeric nomenclature because this is going to be independent of I minus 1, I plus 1. It's going to refer to upwind, far downwind values, etc. So C is the upwind value relative to F. And this is the far upwind value relative to F, and this is the far upwind. This is the downwind value. And this is for if you're sitting on F and your velocity is in the positive direction, this is what this grid looks like. If the velocity is in the other direction, then this becomes C, this becomes U, this becomes D, etc. Okay? Now, all of these schemes work with the alphabetic nomenclature, and then you can apply them to a numeric nomenclature depending on the case you're dealing with. But this is a way to kind of generalize the idea. So with the K scheme, we define two slopes, an upwind scheme based on the two upwind values, phi C and phi U. We call that S minus for upwind. And we define a downwind slope based on phi downwind and the phi upwind value. So all our schemes, we want them to be upwind biased, okay? Because we know these are hyperbolic laws. Things go from the past to the future, okay? And this is the downwind slope. And then we're going to say, hey, we're going to combine these two slopes somehow and weigh them by a parameter k so that we get the value of f, of phi at the face. Why do we need the value of phi at the face? What? Yes, to evaluate the flux. Remember, in the finite volume form, we're doing an integral over the flux, and that results in the integral of the fluxes over all the surfaces of the control volume. In this case, it's flux on the east face minus flux on the west face, okay? But in general control volume, we're going to do a summation over all the fluxes. And the flux is the velocity, for the convective flux, it's the velocity times the quantity phi. And so the velocity is assumed to be known at the interface. If you don't know it, you just interpolate. But it's the value of phi that matters on the face, okay? So that's why we need phi f, the value of phi on the face. And we say that the value of phi at the face is the average value of phi at the cell centroid plus delta x over 2 times a slope s, which is going to be a profile for phi, for the variation of phi in this cell, okay? And then we say our slope is just a weighted combination of the upwind and the downwind slopes, okay? If you use k equal 1, you're going to get the downwind slope. If you use k equal minus 1, you're going to get the upwind slope. And with a bunch of other k's, you get all sorts of interesting schemes, okay? So for k equal minus 1, you get this SOU, second order upwind. K equals 0, you get the from. We discussed those earlier. For k equal half, you get the quadratic upwind interpolation. And k equal 1/3, you get the third order upwind. So FYI, quick is third order, not fourth order. Quadratic is kind of confusing, but it's because we're fitting a quadratic profile. But it's third order in space, third order accurate. OK. And what I'm going to do now, I'm going to spend a few minutes. Actually, I did show you some animations. These are actually wrong. I had a typo in the simulation, but the point, I had a bug in the code. But the point is, no matter what scheme you use, you're going to get oscillations like this. So what we're going to do, we're going to discuss why these oscillations occur, how to fix them, and then we're going to go ahead and program the K scheme, and then program how to fix these oscillations. Okay? And we went through a bunch of observations for monotonicity. We observed that low-order schemes, such as Upwind, are very diffusive, but they preserve monotonicity. They do not oscillate. But any high-order scheme, they are more accurate, but they do not preserve monotonicity. And we talked about Godunov's theorem, which says the other way around. Okay, come on. Come on, it's like I didn't teach you anything in this class. Come on, guys. Godunov's theorem says that you cannot have a high-order linear interpolant that is monotonic, that preserves monotonicity. To preserve monotonicity, the only order you can do is first order. Anything higher is not going to preserve monotonicity. But the key word here is linear, a linear scheme. So to save the day, we're going to look at nonlinear schemes. Okay, and what does that mean? We're going to see today. Okay, and this is Godunov's theorem. Tells you that monotone behavior of a numerical solution cannot be assured for linear finite difference methods with more than first order accuracy. So if you want, that's why all the K schemes, second order upwind, third order quick, they all produce oscillations because they're more than first order, second and third order. Okay. Okay, so we went ahead and proved the theorem, etc. Let me skip some slides. Please review these slides. This is very important. Otherwise, you're not going to understand anything I'm going to be talking about today. And then I asked the question, why do we get oscillations? So we understand from the modified equation analysis that oscillations come through a dispersion term, a third derivative. Today I'm going to show you a kind of more of a qualitative way of why we get oscillations, and it all has to do with the slopes, with the profile that you assume for phi inside the cell. So it turns out that any profile you assume that is non-constant, that's not a zero slope like the upwind. So for the upwind scheme, you're assuming a zero slope because you're not assuming any variation inside the cell. You're saying, hey, the value at the face is equal to the value. You're saying the value at the face is equal to this value. So the slope is zero. Okay? So any other slope, Godunov's theorem tells you, is going to produce oscillations. So why is that? Let's take the second order upwind scheme, and we want to apply it at this cell. Okay? So for this phase, the second order upwind is going to give us this slope. So it's going to produce the same value as this guy, so that's not a problem. But for this phase, the second order upwind is going to use these 2 points, is going to create a negative slope over here. Now, qualitatively looking and thinking about this, this is going to produce a value for phi that is less than this value. So you produced a new minimum over here. And that is, and then once you put things together, it's gonna lower this value just by a little bit. Okay? So you've produced a new minimum that didn't exist in the solution. And that's why these things happen. So what we really want is to modify this slope. What if we can make this slope kind of look like this, such that it doesn't undershoot? Okay? But can we do that? It's a little bit more complicated. One choice is to say, hey, let's pick the smallest of the two slopes. And that's actually called the min-mod limiter. Okay? So you say, how is my solution changing in space? And I'm going to pick the smallest of the gradients. But still, this is not a universal way of doing things, because we need a way to measure monotonicity or how smooth the solution is. Okay, we need a universal way to measure monotonicity, and this is why we get oscillations. Okay. So why do we get oscillations? Okay, this is why we get oscillations. All right. So a negative slope in this case will lead to a volume average less than 1. Now we can always set the slope to be 0, which would give us upwind, but then we lose second order accuracy. So what do we want? we want in, here's what we want. In non-monotonic and high gradient regions, such as this sharp interface that we had, this kind of sharp step function, we want to switch to upwind. We want to set the slope to 0. But in smooth regions or in regions where the function is monotonic, okay, we want to go to second order. So how can we combine the two? Well, it looks like we need a universal way to measure monotonicity. Because if we know where we are monotonic, we can choose a second order scheme. If we know where we are non-monotonic, we'll choose upwind, right? That's kind of the idea here, right? Okay. So we were going to look at two popular approaches to measure monotonicity. One of them you've probably never heard of, but that came out from the group I worked with for my master's, and they really, well, it didn't come out, it wasn't invented by them, but they took it to the limit. It's very intuitive, and it's called the normalized variable formulation. And the second one is the total variation diminishing framework, which you've heard of, the TVD scheme. They are equivalent, okay, but each one of them has a different perspective. So today we're going to look at the normalized variable formulation. And it's essentially just a tool to understand and design monotonicity preserving high order schemes. Okay, so I put these in red because I'm going to give these a name. And I'm going to call these high resolution schemes. So every time I tell you, I say I'm going to use a high resolution scheme, it means I'm using a monotonicity preserving high order approximation for the fluxes. We're just only talking about the fluxes. Okay, we're just only talking about the fluxes over here. All right. If I say high order, you're probably gonna be producing oscillations. So high resolution is monotonicity preserving and high order scheme. Okay. All right. So we said we need a way to measure monotonicity. We can say, well, if the value of phi is between phi upwind and phi downwind, but that doesn't. We want something. We want a way to say, well, if some value of phi phase is between 0 and 1, then we are monotonic. Otherwise, it's not monotonic. That's what we want. So we want to normalize things by the upwind and downwind value. And Leonard, that's the guy who invented this approach, introduced this function. He called it. We define phi tilde as the value of phi minus phi upwind over phi downwind minus phi upwind. Okay, so if you are at cell C, phi tilde C is going to be equal to phi C minus phi upwind over phi downwind minus phi upwind. Okay, and that's just one way to normalize things. You can normalize. The TVD framework normalizes in a different way. But this is one way to normalize. And essentially, it's what it's doing, it's taking the ratio of the gradient. So if you take phi c minus phi u, it takes the ratio of this gradient over that gradient. Okay? It tells you how we are changing as we move in space. Okay? So we define this phi tilde as phi minus phi upwind over phi downwind minus phi upwind. Now, obviously, we are interested in phi f. Okay? And what we're after is phi tilde f, which is phi f minus phi upwind over phi downwind minus phi upwind. Now, what happens when we make this normalization? Because phi f, don't look at this, because phi f is a function of phi upwind, phi far upwind, and phi downwind. So think of the K scheme, the second order upwind, third order upwind. Those are the most popular. I mean, you can have a much wider stencil, but for these cases that have this 3-point stencil, phi f is only a function of phi upwind, phi far upwind, and phi downwind. When you do this normalization, what happens? You turn phi tilde f into only a function of phi tilde upwind. Okay? So rather than having a 4-dimensional space, phi f and 3 values of phi, you only now have, you've transformed this space into a 2-dimensional space, phi f versus phi c. Okay? Now, I claim that this phi tilde, this thing, is a measure of monotonicity, is a clear measure of monotonicity. So let's see how. Okay? So we're going to assume a bunch of profiles in real space and transform them into tilde space and see how the value of phi tilde changes, and then decide where we are monotonic and when we are non-monotonic. Okay? So the first case, let's say you have this situation. You have obviously a non-monotonic function over here, where phi upwind is greater, where phi u is greater than phi c, but phi c is less than phi d, and also phi u is less than phi d. Okay? Or phi c is greater than phi u and phi d, and phi u is greater than phi d. Then when you do the transformation, both of these cases are going to look like this. Now, phi tilde u, what is phi tilde u? Is 0, always 0, because it's phi minus phi u over phi d minus phi u, or phi u minus phi d minus phi u, right? So the numerator is 0, so phi tilde u is always 0. What is phi tilde d? You have a question?
So this, when you're talking about phi tilde u, it's not the same, not nomenclature, but I'm thinking of anytime you have a u, you're thinking of an upward one.
Far upwind. Far upwind. Yeah. If you take the cells in this layout, this is a cell. This is the upwind with respect to C, and this is the downwind with respect to C, right? Phi tilde upwind, the value of phi tilde upwind is always 0, because that's the normalized value. You don't need to. Why do you want to look at the next upwind? I don't understand.
Anytime I see upwind, like if you're at the upwind, or if you're at that cell, upwind is always one over.
You're at this cell. This is the upwind, right? So remember, we are interested in evaluating phi f, which is right here. Okay? And with the nomenclature we chose, this is the upwind value, this is the far upwind, and this is the downwind value. But phi f is over here. Now, what I'm interested here is trying to prove to you that the phi tilde nomenclature is a measure of monotonicity. Okay? It's going to be a normalized measure of monotonicity. And we're going to show that if phi tilde is between 0 and 1, then you are monotone. Otherwise, you're not monotone. Okay? So I'm going to take a few examples to show how phi tilde, when phi tilde is monotonic and when it's not monotonic. So obviously, when phi tilde is less than 0, we are non-monotonic, which is correct, right? Because we started with non-monotonic functions. Okay? Let's take another case. This is another case where we switch the orders here, where phi upwind is greater than phi downwind, and phi c is in between. Well, it's less than the two of those. So notice that here, phi c is either less than both or greater than both. Over here is the same situation, but phi upwind is greater than phi downwind here, and phi upwind is less than phi downwind over here. The point is, once you transform this into phi tilde space, phi tilde upwind is always 0, phi tilde downwind is always 1, and now phi tilde c is greater than 1. Okay? So now we know that if phi tilde is less than 0, we are non-monotonic. If phi tilde is greater than 1, we are non-monotonic. Okay? Because those are non-monotonic functions. All right, so now let's look at two border cases where we are monotonic, but in this case, phi d and phi c are equal. Okay? So what happens? This is kind of the border at the boundary, at the edge of monotonicity of for phi tilde. Phi upwind is always 0, phi downwind is 1, and in this case, phi tilde is 1. Okay? So phi tilde is monotonic, but that's kind of just at the boundary, okay, in this case. And this is the other case where phi u and phi c are equal. So that gives you phi tilde c equal to 0, and is still monotonic. And the classic general case, so what we conclude from this is that when phi tilde is between 0 and 1, it's monotonic. When it's less than 0 or greater than 1, it's non-monotonic. That's what I'm trying to prove here, is that phi tilde is a good measure of monotonicity. Okay? Is this clear? So we've shown that for all the monotonic cases, phi tilde is always between 0 and 1. Okay? Otherwise, it's either less than 0 or greater than 0. So this is going to help us say when phi tilde is between 0 and 1, go second order. Otherwise, go upwind. That's it. That's what we're going to do now. Okay? Now, notice one more thing, though, that I said that phi f is here, right? It's the face, it's the east face of phi c, right? So phi f is actually always, for monotonicity, phi f is always going to be between phi tilde c and 1, right? For monotonicity, the value of phi f is always greater than phi tilde c and less than 1. And that kind of makes sense, right? Because if you don't want to create a new minimum or a new maximum, the value at the face cannot be less or greater than the upwind, than the values that straddle the face. Otherwise, you're creating a new minimum or a new maximum, okay? So keep that in mind. For monotone behavior, actually, the value of phi at the face is between phi tilde c and 1. Now, phi tilde c can go all the way to 0, and that's fine, okay? But for monotonic behavior, if phi c is between 0 and 1, phi f is between phi c and 1. Okay. So let's see how some existing schemes transform into the normalized variable formulation. If you take the upwind scheme, we said that phi at the face is equal phi upwind. Then phi tilde at the face is equal phi tilde c. This is really important because that defines the boundary for phi face. The worst it can be is phi c. Okay? That's when we drop order. For the downwind scheme, phi f is phi downwind. In normalized form, it gives you phi tilde f equal 1. For the central scheme, phi f is this guy in non-normalized space. In normalized space, remember, we said that phi f is always going to be a function of phi c only. Phi tilde f is going to be a function of phi tilde c. Okay, that's what's so great about the normalized variable. Because you can think about it in terms of just one variable, phi tilde c. That's it. If we were looking at the quick scheme, the value of phi at the face is a function of phi downwind, phi upwind, and phi far upwind in non-normalized space. But in normalized space, it's only a function of phi tilde c, of the upwind value. And once that normalization is really useful because it's just saying, okay, how does the value of f, the normalized value of f, is only a function of the normalized upwind value. And we know if the normalized upwind value is between 0 and 1, we're monotonic. Okay? So now, given all of these, what do we do next? As I tell my numerical method students, once you have an equation like y equal f of x, what is the first thing you do? You plot it. You plot the hell out of it. Okay? So now let's plot all of these on what is our diagram going to look like? What's on the x-axis? Phi tilde c. And what's on the y-axis? Phi tilde f. Okay? Lo and behold, what's called the normalized variable diagram. Don't be confused by all the straight lines. FYI, all the schemes are just straight lines. Okay? But something beautiful emerges. So we're plotting phi tilde f. Sorry. You know, we landed on the moon like 60 years ago. You'd think we'd have better technology for projectors. It just needs a moment to cool down. Okay. Kind of killed the flow and the energy. Okay, so let me address some of the confusion, because you're all confused now, obviously, because we created something out of nothing, and you're like, wow. It's not a big deal. Phi tilde f is only a way, the tilde nomenclature is only a way, it's just a transformation to allow us to look at how the function varies. But rather than thinking about phi d and phi up and phi down, is this larger than the other one, is this smaller than the other one, we're just thinking of things in terms between 0 and 1 and less than 0 or greater than 1. That's it. That's the power of normalization. We can always go back. We're going to have to go back to the non-normalized space to compute actual functions. But in the normalized space, it's so much easier to reason about monotonicity. Okay? Okay, so we're going to plot phi tilde f versus phi tilde c. Okay, let's start with the upwind. The upwind said phi tilde f is equal to phi tilde c. So that gives you this line, 45 degrees. Okay, gives you this line. Passes by 1, 1. The downwind scheme was phi tilde f equal 1. Whatever phi tilde c is, phi tilde f is always equal to 1. So that's the downwind scheme. Okay. Now you go ahead and plot all the other schemes: central, second order upwind, from, and quick. And they look like this, but they all pass through this point. Now there's something magical about this point. You can prove that for a scheme to be second order, it needs to pass through this point, 1 over 2 and 3 over 4. Okay. Anyway, but they all pass through this point. Now, they just are curves inside this diagram. Okay. Now we kind of know already intuitively when, not intuitively, from what we've seen, that when phi tilde c is less than 0, we are non-monotonic. So all this region is non-monotonic. Okay. And we know also that when phi tilde c is greater than 1, we are also non-monotonic. Okay. So what this is going to lead us to is, in fact, that everything outside this triangle is actually non-monotonic. Okay? All right. So let's keep thinking about this. Now, for a scheme to preserve monotonicity, maxima and minima in the solution must be maxima must be non-increasing and minima must be non-decreasing, or you cannot create new maxima and or new minima. Okay? So in terms of non-normalized space, to make sure we're not creating new minima and maxima, phi f cannot be greater or smaller than, phi f needs to be between phi upwind and phi downwind. Otherwise, we are creating a new maximum or a new minimum. Okay? That makes sense, right? It cannot be a value greater or less than the upwind or the downwind value. Now, when you normalize this with the normalized variable formulation, everything turns into functions of phi tilde c and 1. And we just noticed on our diagrams that phi f is actually bounded from below by phi tilde c. This actually proves it. But we're bounded from below by phi tilde c and 1. Okay? Okay, so that tells us now, that leads us to a criterion on how we choose when we switch schemes between upwind and high order. So that's what we're after. We're after a recipe that tells us when do you switch to upwind and when do you switch to high order. We kind of know it already. When we are less than 0 and greater than 1, we want to switch to upwind. Otherwise, pick whatever scheme you want. But let's formalize this a little bit. This is called the convection boundedness criterion. Okay? And it says for a scheme to retain boundedness, its functional relation, so essentially phi tilde f equal a function of what? Should be continuous. Could be piecewise continuous. That's fine. But you have to be continuous. Okay? So phi tilde f as a function of phi tilde c, you have to be continuous. It needs to be bounded from below by phi tilde c. So that upwind line, the upwind line, we can at worst be upwind. Okay? We need to be bounded from below by phi tilde c and bounded from above by unity, right? Because we cannot be greater than 1. We have to be bounded from below by phi c all the way until phi tilde c hits 0. Below that, we have to be upwind. So phi c again, phi tilde c. Okay? Should pass through the points. Now this is very important. On the NV diagram, normalized variable diagram, all schemes have to pass through the points 0, 0, and 1, 1. That is the key thing that is going to make us not oscillate. Okay? So the point 0, 0, that's at the bottom. So think of the upwind line. All curves have to start with the upwind and end at the upwind, but can be anything in between. Okay? And be upwind otherwise. Okay? So if you think of phi tilde as a function of phi tilde f as a function of phi tilde c. Okay, we want to make sure that if phi tilde c is equal to 1, then this guy is equal to 1. If phi tilde c is between 0 and 1, you can be whatever you want, because you are monotonic. So you can be second order, fourth order, 10th order, whatever you want. Okay? If phi tilde c between 0 and 1, assuming that you are monotonic, of course. Okay? Now, if phi tilde c is equal to 0, then f of phi tilde c is equal to 0. And otherwise, you are upwind. So you need to hit the points 1, 1, and otherwise, you're always upwind. Okay? So let's look at this in this normalized at the NVD, the normalized variable diagram. This is the monotonic region. And if you think of a scheme phi tilde f as a function of phi tilde c, you're going to have a relation between phi tilde f and phi tilde c. It could look like this. Okay? In this region, we don't care. You can be whatever you want here. As long as once you hit phi tilde c equals 0, you can drop to 0. And once you hit phi tilde 1, you're going to go to 1. And then you go upwind otherwise. So that's the key. If you think about the central scheme, it kind of looks like this. Kind of looks like this, goes through this point. It's these two guys over here that we want to get rid of to make sure that we are upwind outside the monotonic region. Okay? So what? Well, we can now take this normalized variable diagram and design high resolution schemes. That's it. We can choose any functional relation between phi tilde c and phi f as long as it satisfies the convection boundedness criterion. This f could be any set of curves inside the blue region, inside the blue triangle, as long as it goes to 0 and then upwind, as long as it goes to 1 and then upwind. And that's how we guarantee that we are not creating new minima and maxima. It's kind of a little bit, you have to think of it in the normalized space. If you think about it in the real space, it's going to turn into a debacle. Okay? You're going to have a lot of options to think about, like how do I limit the slope here? What do I do with the flux over here? What if this guy was, what if phi upwind was less than phi downwind and phi far upwind was greater? It gets really confusing. With the normalized formulation, you're only thinking about phi tilde c. Okay? So let me give you a first example. It's called the bounded central scheme. So this is the central difference scheme is given by phi tilde f. This is the functional relation, the current existing functional relation for the original central difference scheme. It's phi tilde f is 1 over 2 phi tilde c plus 1. So it gives you this line. Okay? The CBC, the convection boundedness criterion, tells us we are okay over here. But outside, this is not going to work. Because outside, this guy needs to go to 0 and then go like this. And over here, we cannot continue on this path. We have to go on that path. Okay? Otherwise, we are filling in or taking out of the cell more than it is providing. Okay? So what happens when we do the CBC? We apply the CBC. This is what happens. And that's a nonlinear scheme. Because it switches, it changes arbitrarily inside the domain. And we're not even thinking about the sign of the velocity or the gradients. You're just saying, hey, if phi tilde c is between 0 and 1, then do central. Otherwise, go upwind. Yes? It's OK. You can either. I mean, I typically, well, they're consistent, right? Because at phi tilde equals 0, okay, you're going to pick this value anyway, okay? Or if phi tilde equals 0, you're going to get to a 1/2, which is still in the bounded region, okay? Yes?
So I thought before you said that at phi tilde c equals 0, you have to be 0.
So yeah, so you can change that.
So you don't.
Because we never hit 0, and we never really, in practical situation, we're never going to hit 0. So you can just make it greater than, okay? You can make it greater than. Okay, it's not an issue. Don't lose sleep over it. So we're trying to really make it kind of piecewise continuous. Now, the problem, this scheme is still problematic. Okay, we'll show you better schemes now. But this is kind of how you take a existing scheme and make it bounded. Okay, so then you can take the quick scheme and make it bounded. You can take any of the other schemes and make them bounded, as long as you satisfy this CBC criterion. Here's another one called the, well, okay, there's one more thing to say that I need to say, that you want to try to avoid sharp angles in when you're making these turns. You want to try to avoid sharp angles because they lead to convergence issues. So you kind of want to change smoothly as you go through the region. This is another scheme called the min mod. You've probably heard of this if you're working with the TVD framework. But this is what it looks like in the NVD formulation. Notice inside it's piecewise continuous. Doesn't matter. You know, you can have multiple stops in between, and you know, you can argue for why you want to make these stops based on different problems. You know, I'm not an expert in that, but you can refer to the papers and see kind of where this works better for shocks or for skewed, steepened waves, etc. But they're very easy to implement. And this is how you implement them. The practical way of implementing them is you first compute phi tilde c, okay? And then based on phi tilde c, you compute phi tilde f, and then you extract phi f from the definition of phi tilde f. Right? So phi tilde f is phi f minus phi d, or minus phi u over phi d minus phi u. Okay? You have phi d, you have phi u, you have phi c, you have all of these values. You just extract phi f out of that. Okay? So now let's see how this looks like. If you remember, this was, I don't remember showing you this this particular simulation, but this one goes nuts with any high order scheme. Okay? What happens? So what's happening, this guy is acting by the sharp gradients, or over here you have non-monotonic behavior, right? Because your function is going up and then going down. So that's why it starts acting in this region, okay? And if you choose your number of points in a way that you're perfectly symmetric, you're going to be non-monotonic, right? You're going to have two cells, or even asymmetric. You're going to be non-monotonic. Okay, so that's why it acts in this region. Okay, but otherwise we are retaining second order everywhere else. Okay. This is another scheme called the Osher. Okay, and it looks like this. So think of this as phi tilde f versus phi c, and we are upwind everywhere outside the non-monotonic region. Within the monotonic region, you can be whatever you want. So we choose this line. They all have to pass through this point, 1/2 and 3/4, for second order accuracy. And then this is what you get. So it's a simple implementation of the formula. This is not a very good scheme for this case. This kind of skews things a little bit. And why is it skewing things in this direction? Because of this large downwind bias over here, right? There's a significant bias to downwind at the top, right? Okay. This is the muscle scheme. You've probably heard of that as well. Monotonic upwind scheme for conservation laws, Van Leer. It has some upwind bias over here, and it's kind of nice and uniform in this region, and then drops to 0. Okay. So what does this look like? Let's see. Get back. Very nice. Has better behavior in this region. It's not as diffusive, and better behavior compared to the min mod. Okay, but it's a little bit more complicated to implement. You know, once you have a recipe for those, you can just put them in very fast. The infamous super B. You've seen the super B on the TVD diagram, and I'm sure none of you understood the TVD diagram, but you're going to learn. Does anyone know how to interpret the TVD diagram? Okay, so it's very similar to this guy. It's a different normalization. But with the NVD formulation, it's nice and compact because you just have this triangle. Okay? And this is what super B looks like. And really, you know, when you look at this, you're like, yeah, you know, when phi c is between the value of 0 and 1/2, we have a certain slope, and then when it's between these two values, it has different slope, then goes downwind, okay, and then upwind everywhere outside, okay. You want to try to avoid being upwind in this region because you want to maintain second order, okay? You want to try to be as second order as possible. And the stoic scheme is very similar to the upwind, except to the super B, except it doesn't cut here at 2/3. But it's kind of the same structure. So you implement one, you can implement the other. Okay. I know this is a little bit still kind of confusing to you. Well, what did we do here? You know, all we did, think of it as we tried to measure monotonicity, okay? And we said, so we first said, in non-monotonic and high gradient regions, or when slopes change sign, you are non-monotonic. When a slope changes sign, you go from 0 to negative, or from 0 to positive, or from positive to negative. You are non-monotonic, okay? So in those regions, we want to be upwind, okay? Because we know that it's on those regions where we create oscillations. But in smooth regions, higher order schemes are not a big deal. They preserve monotonicity because you're smooth. You're already monotone. They're not going to create a new minima and maxima. Then we said, can we combine the two ideas and break Godunov's theorem, which says linear schemes of order higher than 1 cannot preserve monotonicity? Well, let's combine the two in a nonlinear fashion. It turns out we can preserve monotonicity. It was a revolutionary idea. No one even, when they thought of this, like, yes, this is great. We can use a nonlinear scheme. When we are in non-monotonic regions, let's go upwind. When we are in monotonic regions, let's go high order, okay? And it just works beautifully, okay? So what I'm going to do now, I'm going to spend some time writing code with you. We will start with the, okay, I want you to get your laptops out. And monotonicity preserving. No, we're not higher order in space and throughout the domain, because in certain regions we're going to be upwind, certain regions we're going to be second order. So the global order, you may argue, is still, yeah, but it's the worst order in your domain, right? But spatially, you're going to commit this error only at a time step, in a single time step. You're not going to carry that error along. And so, you know, if you end up having smooth solutions, you're going to be second order in space at the, you know. So, but they behave much better. At least they give you second order locally in space when you are smooth and monotonic, okay? Let's see. Okay. So I am going to have to mirror my slides, localhost. Let's see. You know, there's an even probably better. No one explains this so well, and I spent last week trying to come up with ways to explain it even better, and hopefully next year it will be even better. But I hope at least you now have a slightly better understanding of flux limiters. I know you've used them. I know you've heard of them. But hopefully now you have a slightly better understanding of why we get the oscillations and what we're trying to do with the flux limiters. I think the NVD formulation, or the NVF, the normalized variable formulation, is much more intuitive than the TVD formulation, which we're going to discuss next week. And by the way, on Thursday, let's do the presentations in the class time, so that those of you who want to leave can leave in time and after class. So let's just do the presentations at the beginning of class. We do 10 minutes each. If you can shorten it, even better. But we'll have about 10 minutes, and then we'll spend some time on the TVD formulation. Okay? So no need to stay an extra hour after class. Okay? I know you have commitments. You'd rather be, working on other things. Okay? Okay. Let's see. Second here. All right. So I've also been working on a way to do animations. I was sharing this with Mokbel, and he got really excited. But essentially, rather than what's annoying about these convection schemes in periodic cases, you see it move and exit the domain and then enter again. And then I thought, why don't we ride in a reference frame moving at the same speed as the signal? So you do that, and what happens, you get a frozen simulation. Okay, so let me show you kind of what I mean by that. So, oops, hold on. Okay, so this is the from scheme, what I'm going to show you now. So this is the from scheme, and what I'm doing here, I have a wave moving to the right, but I'm also moving at the same speed as the wave. So it looks like it's just stationary, okay? But still, that's kind of nice because you just can see, just focus on one spot and see the oscillations. But to give you the impression that it's actually moving, what I did yesterday, I actually moved the background. So look at this. So I'm still moving within the same reference frame, but I'm moving the x-axis on the back. Anyway, but this is still this is a flux limiter, or we can start calling them limiters, okay? Because we're limiting the fluxes, right? Okay, let me get a new. Okay, so let's first start by implementing the K scheme. Okay, and I'm going to create a new notebook. Let's go ahead and create a new notebook. The K scheme in class. Okay. What? Okay, so I have some pre-typeset text that, of course, is not going to work because Python sometimes barks. Okay, let's see. Of course, it's going to bark. Okay. Sorry about that. I don't know why Python and math and LaTeX are not very good friends. Let me show you the K scheme on. First, let me remind you of the finite volume integration, what we're going to do. So we're integrating this equation. d phi by dt is minus df dx, and f is a flux. So this is in conservation form. In this case, f is u times phi. We're going to take u to be constant in these cases, but it doesn't have to be constant. And then we integrate in space and time. And so you integrate in space, and then you assume this is the average value here. So you get d phi dt, d delta x. And this guy just integrates in space. You get the difference between the east and the west value. But then the time integral of the flux, I'm going to call this f tilde, and f tilde is this guy. And we said last time that we're going to need a high order time integrator, so that we went ahead and approximated the numerical flux at the faces using the midpoint rule, which is which gives you the value of the flux at n plus half. But we don't have n plus half, so we need a two-step method. So you do a predictor. Okay, you do a predictor. at half a step, and then you correct it. Okay? So that's what we're going to implement here. Now, at this step for the predictor over here, Fn, you can use a low order flux. So I'm going to use Upwind in that case, okay? Because it overcomplicates everything. It's not going to affect your accuracy. You can use Upwind in this predictor, but in the corrector you have to use a high order, the high order flux. And for the high order flux, we are going to go. We are going to go with the K scheme, okay? So this is what we're going to do for the high order flux. So we're going to go and visit every face in the domain, and for each face we're going to find the upwind, the far upwind, and the downwind values, and we're going to calculate this value. So this is going to change the way we have done discretization and numerical implementations before, because now we not only have arrays for the cell-centered values, we also have arrays for the fluxes. But how many arrays for the fluxes do you need? One array. You don't need the east flux and the west flux. You just create a flux, because the east, from the perspective of the cell, yeah, you have two fluxes, but from the perspective of the fluxes, you just have that one face, right? So we're going to visit each face and fill the flux with this value, and then take the difference of the fluxes at the cell centers, okay? Classic finite volume methodology. Okay, so I'm going to go back to this guy and going to import some stuff from my code over here. So I'm not going to go through this stuff. Okay. I'm not going to go through this anymore because you guys are intelligent and know how to do this. And I'm going to define a couple of functions here to give me the nice Gaussian and step function representation. It's these guys, so you can go through this at home on your own time. Now we start putting in some boilerplate. So I'm going to define L equal 1. So that's domain length, okay? And number of points, let's say we do like 250, 256. So these are cell-centered points, okay? So then dx is really L over n, not n minus 1, right? Because this is finite volume. These are the cell centers, or the intervals, okay? So number of intervals, if you want. Intervals, cell centers in FP formulation, okay? So dx is L over n. When we were doing finite differences, we were looking at n as the number of points, and then you had n minus 1 intervals, okay? So don't confuse the two. Okay. Now, because I need the far upwind and the downwind values for the faces, I'm going to put two ghost cells in this domain. Because the K scheme is so general, it's going to either require, phi C and phi upwind, so that gives us 2 points, right? Or if the flow is in the other direction, we're going to require 2 points on the right-hand side. So we're going to add two ghost cells on each side, okay? So I'm going to create a linear space that includes those 2 points. So X is mp.lin space. Okay, let's see. Where does, what is the first? So this is the cell, this X is the cell centroid X coordinate, okay? So where do we start if we have two ghost points on the left? So the boundary is at 0. The first interior cell is at delta X over 2. Correct? The first ghost cell is minus delta X over 2. And then add one more, minus delta X. So that's minus 3 delta X over 2. Agreed? Okay. So we're going to start from minus 3.0 times dx over 2. And we're going to go to L, which is the edge of the domain, plus two ghost cells, plus delta X over 2, plus delta x. So L plus 3 delta x over 2. Okay? L plus 3 times dx over 2. How many intervals? So how many? So we have n plus 2 on each side, so n plus 4. Okay? So if you kind of want to see how this looks like, let's say we have 10 intervals, and then print x. This is what you get. The first interior point is delta x over 2 inside the domain, right? We're not at the boundary. We are half a delta x inside. These are the cell centroids. Okay? It's default true. Yeah, by default it's true. Okay? And you can see this is the minus the L minus delta x over 2, and this is L plus delta x over 2 and L plus 3 delta x over 2. Okay? So if you look, you asked me this in the past, Mokbel. If you look at endpoint, it's true by default. Okay? Okay. But good observation. I mean, you want to make sure that you have things correctly implemented. Okay? All right. So let's go back to 256 points. Now we're going to create a bunch of arrays. So okay, create solution arrays. We're going to do phi is np.zeros. How many points do we have? N plus 4, right? N plus 4. Okay. Now, for the fluxes, I'm going to call it flux. How many points do we have for the flux? So let's count. Okay, so let's say these are the interior cells. Okay, so we're going to need a flux over here, correct? Or not? Well, I'm going to store a flux over here because I just want to rip through the array. Whether I use it or not, I'm probably not going to use it because I'm not actually going to use it because I'm going to be periodic. Okay? So it doesn't matter. But for the fluxes, if this is 1, 2, 3, 4, at least for the interior of the domain, what do I have? I have 1, 2, 3, 4, 5. So I always have n plus 1. So if I have n cells, I have n plus 1 fluxes. So in this case, what I'm going to do, because I don't know how I'm going to use the flux, I have n plus 4 cells, so I'm going to do n plus 4 plus 1 values for the flux. Why am I doing this, though? Although I'm not going to be using the flux value over here, it's going to help me with the indexing. If I start the flux indexing from here, 0, while the cell indexing is 0 over here, then when I get to compute this flux, this cell reference is going to be 1, and this cell reference is going to be 2, and this one is going to be 0. It's going to be confusing. Okay? So I want my flux indexing to start similar to the cell indexing. Same reference. Okay? It's just a convenience. Okay? Don't lose sleep over it. You can do it however you want. But if you do it my way, it simplifies life. Okay? So that's where experience comes from. You can try to hold yourself like this because you think it's cool, but you know, oftentimes you're wrong. Okay? Sometimes I'm wrong, and that's why you come and correct me. Okay? So for the flux, I'm going to put it np.zeros n plus 4 plus 1. Okay? And then for the u velocity, well, I'm going to assume a constant velocity. Okay? We can have a non-constant velocity if you want. That complicates things a little bit for the upwind directions. We're going to assume a constant positive velocity over here. Okay? But before we do this, let me actually plot the solution. So I'm going to take x0 equal 0.3 is just a number. Phi 0 is the initial condition. It's going to be a Gaussian x0 plus a step x0, and then PLT dot plot x. Now I'm only going to plot the interior points, so x from 2 to -2, and phi 0 from 2 to -2. And that gives us this kind of beautiful combo. This is a nice combo to test advection schemes, because you have sharp gradients, non-monotonic behavior, and monotonic behavior. Okay? I guess you guys are stuck over here still, trying to implement this. You don't have to type with me if you don't want to. You can look at it. I'm going to put it on the website. Okay. So now let's define. So I want to move at a CFL 0.5. So I want to move half a step. For each time step, I want to move half a delta x. Okay? I'm going to assume my speed is 1.0, constant speed. Okay? And dt is CFL times dx over c, right? So print dt is equal to dt, print, I don't need dx. Okay, so it's going to give us this time step size, all right? So now we can implement the case scheme. You guys still typing? Caught up? Who is not caught up? You're going to follow afterwards. Yeah. I agree. Just gonna, better. Yep. Okay, the K scheme or kappa scheme, right? And I set K equal -1. That's going to give us, second order upwind? Or no, the upwind scheme. That's going to give us the upwind scheme. Okay. Okay, so T equals 0, T end. So let's make it go through, let's just do like 1 second. Or make it go through one cycle, so L over C. Make it go through the domain once. So if it's moving at a speed c, it's going to take L over C time to get through the domain once. Okay, so that's T end. And because I want to animate things, I'm going to create a solution array, solution equal, etc. And then start by appending phi 0. Okay. Images, so a bunch of images over here. Okay. Okay, let's see what I did here. So I did some acrobatics for plotting that I'm not going to do for you here, just for simplicity. plt.figure, I'm going to create a figure, fig size equal 5 by 3 maybe, and dpi equal 200. And okay, plt.plot, I'm going to put the initial plot, x2 to -2, phi 0 to -2. It's because I want to do an animation, okay? Dark red, that's the color, animated equal true. Okay, never mind these things. You don't have to do these things. Okay. All right. So now we get things solved. So I'm gonna let's start with the classic time advance. Yeah, while t less than t end, what do I want? T plus equal dt. That's my favorite part. Okay. So the first thing you want to do is grab phi n, right? Phi n is solution -1, so that's the last entry in the array of solutions, correct? And then let's apply periodic boundary conditions. Okay, so now we have two ghost cells. I want you to tell me how we're going to do the periodic boundaries. Okay? So if this is for the cell centers, okay, we don't care about the fluxes for periodic boundaries, okay, because they're going to be automatically picked up. So if this is indexing, 0, 1, 2, all the way to n plus 3. Okay, that's I indexing. For Python indexing, this is 0, 1, and this is -1, -2, -3, -4, and this is 0, 1, 2, 3, okay, etc. So how are we going to do periodic boundary conditions? Okay, so we want, let's start with the right-hand side. We want this interior region of the domain to really be here. So we want this guy to be equal to that guy, and this guy to be equal to that guy, right? Okay? So what we want is phi -2, or phi -2 to be equal to phi 2, correct? And phi -3 to be equal to phi 3, correct? Sorry, phi -1. All right, phi -1. Okay? Now what about this guy? We want the interior to be here, right? So what do we fill this cell with? This guy. This guy goes here. That guy goes here. So phi 0 is equal to, what is the index of this guy? -4, right? Phi -4. And phi 1, what is that? -3. I love circular indexing in Python. Okay. Okay. Now notice the sum of all of these numbers is 4, right? In absolute value. Because we have 4 cos. Okay. Maybe you can come up with a general formula for this. Okay. So periodic BCs, this is it. Phi n, I'm going to take phi n and apply the periodic boundaries right here at the beginning. So phi n -2 is phi 2, phi n -1 is phi 3, and then phi n 0 is phi n -4, and phi n 1 is phi n -3. Okay? So we filled the ghost points with interior points at the beginning of the simulation, right? So now I'm going to create a temporary array to store predictor. So we're going to do a predictor, and that's going to be phi is np.zeros like phi 0. Okay. Agreed. Now we do the predictor. Predictor. First, we're going to fill the fluxes. Okay. What are the fluxes? We said the predictor is going to be upwind. That's simple, right? So phi f is phi upwind. Okay. Or in other words, phi f is phi I. Right? So how are we going to do this on this array? I'm going to go ahead and fill only, so going from this guy to that guy. Okay. So going from this face all the way to that face. Okay. Now you understand the reasoning behind my indexing. Okay. So we set for the cell centers, let's erase this a little bit. For the cell centers, we said this was 0, 1, 2, 3, etc. Right? And then -1, -2, -3. For the faces, this is 0, and this is 1, right, for the face over here. And this is 2. Okay. This is 3. all the way to, this one is -1, this one is -2, this one is -3, this one is -4. Okay, so what I want is to go over these points from 2, so I want flux from where? 2 to, remember this is open, -2. Thank you, Aaron. So that gives me this slice, all the interior faces, including those at the boundary. What is the, now the flux is really C times F, right? So the flux is C times phi face. But since C is constant, I'm just going to compute phi face. What is phi face for the upwind scheme? It's phi upwind, the value of the phi in the cell, in the upwind cell. In this case, C is positive, so the upwind cell is the one to the left, okay? So flux, all of these fluxes are going to be equal to phi. Which values of phi? So we want this value, starting from this value, right? Because we started with this face, we're going to start with this value for phi, correct? So phi 1 all the way to which value of phi? -2, yes, because we are open. Okay? That's how we fill in the flux. So it's really saying flux from 2 to -2 is C times phi n, right? That's the predictor case, going from 1 to -2. Okay? That gives us the flux. And now we do the predictor update, which is phi n plus half is phi n minus delta t over 2 minus c delta minus delta t over 2 delta x times the difference in fluxes, right? And the fluxes already contain the velocity. Okay, so you have only dt over dx because the flux now contains the velocity. All right. So what we're going to do next is say at cell I, so phi I n plus half is equal to phi I at n minus delta t over delta x minus delta t over 2 delta x times flux east minus flux west. Now we already have the fluxes stored on the faces, right? So all we have to do is figure out at cell I, we're going to get the flux minus this flux and divide by delta x and multiply by delta t over 2. Okay? So how do we do that? And we're doing this only for the interior cells. So our phi is going to go from the interior cells where? From 2, correct, to -2, right? So that gives me all the interior cells. Agreed? Is equal to phi n 2 to -2. I don't care, right? Minus delta t over 2 delta x. Now what about the fluxes? What is F east? It's going to be which guys? It's going to be this, all the ones to the right of the cell. So we're going to start with flux 3, right? So we're going to do flux going from 3 to what point? To this. I want to get to this guy. So that's -2, right? Correct? Agreed? That gives me the east. That gives me the set of the east fluxes, the subset of the east fluxes. Now from that, I'm going to subtract the set of the west fluxes. So all I have to do is move by 1 to the left. Okay? Flux going from 2, that's the west flux, all the way to this guy, which is -3. Okay? Clear? Right, when you write the numbers, it becomes a piece of cake. Okay? Still have 4 minutes. We can continue next time. Okay. So, okay, so we said phi from 2 to minus 2 is phi n from 2 to minus 2 minus dt over 2.0 over delta x times flux from 3 to minus 2 minus flux from 2 to minus 3. Correct? Good. So that gives us the predictor. Now we want to apply the periodic BCs on the predictor, right? Because we're going to use the predictor to correct it. We're going to correct it. So all we have to do, we copy the boundary conditions, but apply them on phi rather than phi n, right? Okay. So now we get to the actual implementation of the K scheme. For the K scheme, we need phi upwind, phi far upwind, and phi downwind. Okay? So let's see. Phi upwind is only a subset of phi. So remember, we're going over each face. So we're going to start with this face. Actually, let's start with this face. Yeah, we're going to start with this face. And we're going to take all the upwind cells all the way to this guy. So we need this subset from 1 to this guy, which is minus 2. So I'm just going to define a subset of the array to make the manipulation easy. Okay? So phi c is phi from 1 to minus 2, right? Now, what is phi far upwind? Yeah, 0 to minus 3, right? So if we're starting with this face, remember, I don't care about the fluxes in here. So I'm starting with this flux. We need the upwind and the far upwind. So we already got the upwind, the subset of upwind faces. Now the subset of far upwind faces is going to be this guy, from 0 to minus 3. Okay? So 0 to minus 3. And then phi downwind is going to go, you just simply add 1, right? To minus 1. Okay? So that's phi upwind. That's phi far upwind. And that's phi downwind. Okay? Now we can create the K scheme. Finally, if you bear with me. So flux from 2 to minus 2 only on the flux faces that matter. Okay, interior plus the boundary. I don't care about outside the boundary. Okay, only for the faces that matter. So that's from 2 to minus 2. What did we say was the K scheme? Was this guy. It's pretty easy now to implement it, right? Because so that's the power of this nomenclature. Phi c, phi d, etc. So if the velocity is swapped, you just put an if statement. If c is positive, do this. If c is negative, this is the upwind. If you have a varying velocity in the domain, you may have to do an np.where or an if statement. Okay, do a loop. Okay, but otherwise, if you have a constant velocity that can be either positive or negative, you just put an if statement and change the meaning of phi d and phi c. Okay, so this is what we have. Okay, so flux from 2 to minus 2 is phi. Copy this. Phi c plus 1 minus k over 4 times phi c minus phi upwind, right? Phi c minus phi plus 1 plus k over 4 phi d minus phi c. Okay, plus 1 plus k over 4 times phi d minus phi c. This is great. Now you need to multiply by the velocity, right? Because the flux is velocity times face value. Finally, advect. And now we do the full advection. Phi from 2 to minus 2, that's the interior, is phi n from 2 to minus 2 minus dt by dx. That's just a simple Euler step. And what do? We just grab this guy here, It's the same thing, right? It's the difference between the fluxes. But now these fluxes are high order, right? Okay. And then we have t plus dt, and then maybe we add a timer, I plus equal 1. Okay. And solution dot append phi. Okay. Now, for each one of those, what I'm going to do, I'm going to make a plot, and I'm going to say, okay, and let's create a plot, so that I remember how I did it. So let's say if every like 16 time steps, for that's every 16 time step, I'm going to make a plot. Plt dot plot x 2 to minus 2 phi n from 2 to minus 2, correct? That's what I'm plotting, and then animated equal true. Actually, I don't need the initial condition. And then images dot append im. So this is like pretty fast and ugly way to do an animation. And then let's let me see how I did it here. Just do a function animation. Animation is animation dot artist animation, actually. Artist animation on fig, bunch of ims, just kind of interval. And then let's see if this works. Oh, we have an error. Too many indices for array. Oh, yeah, I put a comma. Thanks, Mokbel. Okay, now I is not defined. Oh, I didn't define I. I is 0. Okay, so now it ran. Let's see if we print the animation. Okay, so you see the wiggles. They start up very, very quickly. And let me actually get rid of this. Let's keep the initial condition. And maybe plot at every time step. Anyway, so you can play with the K scheme and see what happens. The animations are just so annoying with these Jupyter notebooks. Anyway, so you can play with it. It's pretty slow, very, very slowly. And keeps changing color. So you can see the wiggles. This is for the second order upwind. Sorry, no, this is, hold on. God, what is this for? Yes, for the second order upwind. So if you go with quick, which is 1/2, so you just change this guy, okay? And let's animate every 4 time steps, let's say. Do an animation. You see the wiggles. They're on the upper right and the lower left. With the second order upwind, they were only on the lower right. Okay, so you see how K changes things, but you cannot get rid of these wiggles.